Hey, it's December 2nd, and since it's the 2nd, I want to do something involving the number 2. And what I want to talk about is something called Azo Spin Symmetry. Azo Spin Symmetry is all about how quarks interact. So there are 6 different kinds of quarks. There's the up, the down, the charm, the strange, the top and the bottom. And in ordinary matter we only have the up and the down. They make up the protons and the neutrons inside all of the atoms that we see around us. Now, early on in particle physics, we didn't really have access to most of the quarks. We could only really reproduce the up quark, the down quark and the strange quark in the lab. And these have been known for quite a while, and nobody really knew how these all fit together in some kind of consistent model. They tried to build symmetries around them, and some of these were very good symmetries and some of them were quite poor symmetries. One of the symmetries that worked very well early on was called Azo Spin. And that said that the up quark and the down quark had pretty much the same mass, and that meant that there's a symmetry between them. It's as easy to produce an up quark as it is a down quark. And then you can use this to predict how often one particle will decay into different sets of particles, and this works very well for particles that have up and down quarks in them. So for example, you can take a look at the delta system and see how often they go to protons and pions and neutrons and pions. And the delta is just an excited proton or an excited neutron. It's got a sort of pion in there, if you like, and they just decay. Now, the problem with isospin symmetry is as soon as you try to apply it to the other generations of matter, the strange charm quarks, the bottom and top quarks, it all breaks down, because then the mass becomes very important. Now, the mass difference between the charm quark and the strange quark is something like 1 GeV. This is 10 times the pion mass, roughly. So the idea that you can treat a charm quark and a strange quark in the same way with respect to isospin is a little bit crazy. And it gets even more broken as you get to higher masses. By the time you get to the top quark and the bottom quark, you suddenly find that there's no way to conserve isospin anymore. You can't use this symmetry to make any kinds of predictions about how often you're going to get a B quark and a top quark. And this leads to some interesting situations if you're trying to work through isospin symmetries, because you can end up changing, for example, a B quark into a U quark, and then you suddenly gain some isospin from nowhere. You try to balance it all out and it doesn't work. So it's really quite amusing for me that we have this symmetry that worked so well for so long, but when you try to apply it to the majority of particles we know about, it fails spectacularly. Now, that in itself isn't particularly interesting. It's a sort of historical accident. But what I want to talk about now is broken symmetries. So there are many symmetries we get in the universe, and it basically is a reflection of the sameness of the universe, if you like. So if you can perform some transformation and things are the same before and after, we call that a symmetry. And that tells us that something is conserved. One of the most famous examples of this is translational symmetry. If we moved everything in the universe 1 meter to the left, everything would still work in exactly the same way. And that gives us conservation of momentum, one of the most fundamental symmetries we have. Now, when we get a broken symmetry, that tells us something even more spectacular about the universe. So, a good example would be the proton and the neutron should have exactly the same mass, if we are to believe the symmetries of the strong force. They don't. They have a very slightly different mass. The neutron is heavier than the proton. And that tells us there's some difference between them that you can't get from the strong force. And that difference is the electric charge. That gives a binding energy to the proton and to the neutron. And for the neutron, the binding energy is slightly lower than for the proton, and so it can decay to a proton and to other particles. And that is really cool. Every time we see a broken symmetry, it tells us something new about the universe. And I'll come on to some of those things in later videos. But anyway, this is all about isospin symmetry. It was a beautiful symmetry when we didn't really know about quarks, and we didn't really understand how hadrons were made. But now we know a lot more about them. It seems like quite an antiquated system, and the violation of isospin symmetry has led to some of the most spectacular results in particle physics. Okay, I'll see you tomorrow.